Yeah, we're on this one. I marker all of these. Okay, so happy Monday, happy November. All right, so let's see where we are at. All right, so this is where we left off right here. All right, we need to finish talking about how we do our experiments. So if we could please put everything else away and focus on this, I will try to get through the notes as quickly as possible. First of all, reminder, we have observational studies and we have experimental studies, meaning we just observe versus there's a treatment. And what we talked about last week is we talked about a completely randomized design for an experiment, but then we briefly talked about a block design. And a block design is used when you pre-sort individuals into homogeneous groups, okay? So it's when you decide that your sample might have some inherent characteristics that might make them react differently to the treatments, okay? So I gave you this example that I found online, which is just if we're testing to see if hot or cold water has more of an impact on our cleanliness when we do our laundry. What I'm going to do here is just kind of go through an example that's related more to the video that we watched about patients who had knee pain. So I made some of this up. I said, let's say there were 650 patients. 50 of them had early onset arthritis, so they were before the age of 50. 200 of them were between the ages of 50 and 65, and the rest were 65 or older. How might you set up a randomized block design? So if you, as a physician, realize that arthritis might, the pain might be impacted by your age, first of all, you need to know how we phrase this. We call this, we are going to block on age, or they'll say block by age. I don't care which of those, but you need to understand that when you say block by or block on something, you are recognizing that this is the criteria that you think is going to impact the results of your experiment, and so you're going to separate based on that. So using the same sort of model here, this says you start with many piles of dirty laundry. We might say that we start with our 650 patients. Okay, so those are the patients that we have in our group. We think that their age is going to have an impact. So the first thing we're going to do, and this is not random, we purposely say, okay, out of those 650, I'm going to separate them by early onset, and there were 50 of those. We have in the middle between 50 and 65. And then we have the people who are 65 and older. So this is less than 50, and this is greater than or equal to 65. So this is 50 up to 65, but not including the 65, but whatever. So you pre-sort that. You pre-sort into those groups, okay? So that is not random. But now each of those has to get a random assignment to the treatments. So I'll just put random assignment. So basically what happens now is you have to fan each one out by 5, because if you remember from the video, there were 5 treatments. There were 2 new meds, there was a combination of the new meds, there was the active control of the old med, and then there was the placebo. So you would now have 1, 2, 3, 4, 5 fanning off of each one of these. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And you can see how messy and complicated it gets right away. So if there are 50, and I made these numbers up so they would divide out really nice too. So you would then say, I want 10 people in each of these. And in this one, if these were the less than less than 50. There were 50 of those. So then this group there's 200 of those. So now what? We need 40 in each of these. And then if there are 50 here, and there were 200 here, that means there are 400 down here. So that means what? 80 in each of these. So you can see, to actually do this experiment in the best way, it starts getting kind of complicated. I know that the diagram is hideous. I know that, okay? Now, if you actually had to describe this setup on a test for me or on the AP exam, this is just the diagram. This is like writing an outline in an English class for a paper. You don't turn your outline in as your final product, okay? You actually have to write the paper, okay? So you would have to be describing what you're doing and how you're doing it. And so when you get to this, you would literally have to be describing, out of the 50 people that I have assigned to the below 50 age group, I'm going to use a random number generator, and I'm going to number my people 1 to 50, and I'm going to randomly generate 10 unique individuals. Okay, they're going to be assigned the first group, and they're going to get the new medication number 1. Okay, then I'm going to choose from 1 to 50. I'm going to get 10 new unique numbers, and they're going to get medication number 2. And then I'm going to randomly generate 10 new ones. They're going to get medication number 3, which is actually the blend. I'm going to randomly generate 10 more, and they're going to get the active control. Now on the last one, you don't need to randomly generate because there's only 10 left, and you would just say the remaining 10 are going to get the placebo. So you literally could say, I'm going to randomly generate 10 unique numbers between 1 and 50, and those 10 people will get medication 1. I'm going to repeat the process 3 more times to assign people to medication 2, 3, and the active control, and the 10 that are left over will get the placebo. And then you do it again, okay? And if you look at, I typed it up here. Now, my numbers are different here. I did 150 instead of 650, but whatever, okay? So I started by saying we assess the patient's knee pain. Remember, we have to start by measuring something. I use a randomized block design, and I block on age. Individuals will be separated into 3 groups: below 50, 50 to 65, and greater than or equal to 65. Less than 50, okay? Now, I changed numbers. Let's say there are 50 individuals. And I said, I'm going to use a random number generator to generate 10 unique numbers between 1 and 50. These 10 people will receive medication 1. Repeat 3 more times. The remaining 10 people will get medication number 5, the placebo. And then I did it for the next group. And I did it for the next group. And then I just said patients will follow all instructions for the duration of the experiment. At the end, we're going to reassess knee pain, and we're going to compare with the original assessments. Okay? It can get long if you have to describe the whole procedure. Okay? It can get long. All right. The next one is called a matched pairs. And a matched pairs is exactly what the name says. You are going to pair up subjects who match. In other words, you're going to pair up subjects who have similar characteristics. Whether it's age, whether it's gender, whether it's skill level, whether it's where you go to school, okay? But you pair up subjects who match, and you use the various treatments, and you compare to each other. So again, the little diagram I have here is just one that I found online. I actually like the other one better that actually has a specific example, like the laundry. But what I liked on this one is it talked about where there is not randomness and where there is, okay? So let's just say I was doing this. okay? And I wanted to pair you guys up according to similar characteristics, okay? I could maybe pick, I really could probably pick you, Lacey and Emma, you're both females, you're both enrolled in AP statistics, you both go to LCM as your home school, okay? So you might be a good matched pair, okay? But so I might say, all right, I'm gonna choose to put Emma and Lacey as my first two subjects. I'm gonna pair them up. But then when I decide whatever is I'm testing, okay, I now have to randomize this. Okay, so whatever it is I'm testing, okay, treatment 1 versus treatment 2, I would have to flip a coin and say, okay, heads will be treatment 1. So I flip a coin, I'm like, oh, okay, treatment 1, treatment 2, okay? And so on the next one, when I decide my next pair, okay, Connor and Kyle, you guys would be a classic matched pair, right? Okay, twins. I mean, by default, that's actually, have you ever read about some of the studies that people have done like in the past, like on twins, like illegally? I'll talk about that in a second. I'll talk about that in a second. But so they would be a great matched pair. So I might say again, heads treatment 1. And I flip a coin, it comes up tails. And I'm like, oh, okay, so you get treatment. So treatment 2 came up first, whatever. But you have to randomize something. So if you are purposely pairing up subjects, you have to you can't just automatically say subject 1 gets treatment 1, subject 2 gets treatment 2, subject 3 gets treatment 1, subject 4 gets treatment 2. Okay, it goes back to the video, the guy pulled the pills out of his pocket, and you might think, well, that was random. He just pulled it out of his pocket, handed it to one of them. He pulled the other one out, handed it to the other person. It feels random, but it truly wasn't random, okay? Random is complete and utter chance. You flip a coin and the coin tells you who gets which pill, okay? So something has to be randomized. Quickly, I don't want to take too long in this, but there was a movie, I don't remember what it was even called. I remember reading about it, and then they actually did like a documentary on it. It happened, I want to say this was originally in the news. I want to say it was probably back in the 70s or 80s, but it came back in the news when this documentary came out. But it was a Jewish adoption agency based in New York City, as I recall. And the bottom line is, twins are, okay, researchers, biologically, they like to study twins because you have a lot of similar characteristics, And what they did at this adoption agency, they actually took twins and triplets and multiple births, and they separated them at birth, and they were trying to do a nature versus nurture. And they separated them at birth and purposely put some of them in well-to-do families and put the other twin in not well-to-do families. And they wanted to see how the twins ended up. And because they said there was such a built-in natural comparison for twins, they thought this was a great way. That was a great way to control lurking variables, right? And now they could really test and see if the environmental factors were the ones that actually had something to do with their success. And the documentary that they made on this, it was actually based on triplets. And one of them had gone to a community college, and he transferred to another college. Something happened. Someone walked by and said, hey, and said hi, and he's like, I had no idea who that was. And bottom line is they realized that his identical brother had already gone to the other college, and someone saw, when he transferred from this community college, they saw him, thought it was the brother. They figured out there was something weird. They brought them together, and the brothers were like, holy crap. Well, and then it made the news. Someone interviewed them, put them on the news, and the third brother saw the news article, saw the news show, and it was like, jaw drops. He sees two identical people. It's like, oh my, so they were triplets. And there was something, and again, I'm remembering just sketchy details, but the researcher, he did something legally that he locked up the results of his study, that he made sure that they could not open the results of the study until X many years later, when he knew a lot of the subjects would long be dead, and then they couldn't come back and sue and things like that. But seriously, look up, triplets, identical triplets separated at birth. I think it was in New York, and it's fascinating. But it was talking about the ethics of, you want to do quality research, but it's a little bit, did you find it already?
Yeah.
Yeah, I said it. They had like curly hair.
Yeah.
Yeah.
It says a documentary 2018.
Yeah, that's why I said, so it just came back in the news a couple years ago. It's fascinating. I mean, it's horrible. Pardon? Seriously, right? We could maybe do that. Seriously, I was fascinated reading this article, and just think, like I said, the whole thing is you want to do quality research, but even the observational study thing that they talked in that video, they said you don't want to disturb an environment. Okay, talk about disturbing an environment right there. They really messed with these people's lives. And so a couple of people have found their twins or their siblings, but they still don't have, I feel like I read somewhere that they don't have total proof that they were part of that study, but they think they were. Mm-hmm. And so a couple of the families have found one another, but anyhow. So, all right, so matched pairs. You want to match up subjects who are similar, because if you're trying to test, and that's a great example, because if you're trying to test how the environment impacts your growth, you want to control all those similar factors, okay? So on this one, I just said an educational psychologist wants to determine whether listening to music has an impact on a student's ability to learn. Students of the same gender with similar GPAs and grades in a stat class are paired up. There's your matched pairs. Gender, GPAs, grades, they're all in stat class, okay? So you're trying to make your partners as similar as possible, because if you are trying to decide if music is helpful or not while you study, you want all the other things, and that actually leads me on to part C. Explain why it might be important to match the students according to GPA and gender. You want to make sure other factors are not confounded with your explanatory variables. So if you're trying to determine if music is or is not the reason for people's grades being good or bad, you want to control all the other things, okay? So if you're trying to decide, like my son loves to have music on while he works. He was at my house last night writing a letter of recommendation. He had music playing in the background. And then he's like, Mom, can you help me word this sentence? And I'm like, only if you turn the music down, because I couldn't even think of like better things to say because I'm hearing the music. Okay, he loves music while he works. I do not. Okay, so here they are trying to decide, is it helpful or hurtful for most people? Okay, so a coin is tossed to decide which student in the pair is assigned a quiet room and which one will study with music in the background. In this case, I would say the control is there's going to be no music, and the treatment is we're going to have music in the background. Okay, where you might say that they're both kind of experimental, but no music is kind of like a default, and then music is something that you would add to an environment. So that would be considered a treatment. What could the researcher use as a response variable? They could just use grades in the class at the end of the semester. They could use grades on a particular test within the semester. Okay, so maybe if I were to conduct this experiment, maybe as we enter Unit 5, maybe I randomly assign you guys that, I put you guys, pair you up, similar grades, whatever, and I could say, all right, when you study for your Chapter 5 test, you won't listen to music and you will. And I could randomly assign who is going to and who's not, and we'll see if it affects your grade. Okay, we could conduct this experiment if we wanted to. I'm not going to, because I don't want to mess with your grades. Okay. But you also should know that when you do matched pairs, you can match subjects onto themselves, which is another way to do it. Okay, if you want to get away from the whole twin thing, but you want to make sure that the individuals they're as similar as possible, you could just match yourself onto yourself. Okay, so subject 1. For one round, you're going to get the treatment. Okay, we're going to randomize when you have the music or when you don't. But we might say for the next test, Unit 5, you're going to listen to music. And then when we get to unit 6, you're not going to listen to music, and we'll compare your results. Subject 2, okay? Randomly decide. On the first one, you're not going to listen to music. On the second one, you will. And you can compare their results, okay? So again, this is not random because we make the choice, we're going to match everyone onto themselves, but you have to randomize which order they get. You can't automatically say everyone's going to start with music and then everyone's going to not have music. Because all of a sudden now you have the lurking variable here is the different tests, right? What if one test is naturally harder than the other anyways? Our next unit is on probability, which is not often people's favorite. Okay, so maybe it's not going to make a difference whether it's music or non-music. Maybe some of you are just going to suck in the next unit. Okay, so how could the educational psychologist conduct the experiment as a match pair design with students matched onto themselves? We could do one test with music and then one test without music. And again, you would have to randomly determine which order for each subject. And you will still have to contend with the fact that there is still that lurking variable, that confounding variable. Is one test just harder than the other? So if you have that in general scores were lower on Unit 5 test, was it really due to the music or the lack of music, or was it just due to the fact that it was probability and people often don't do well on probability? Okay, so it's difficult to determine, with the lurking variables, okay, and it's sometimes uncontrollable. But all right, the last part of the notes, 4.3, is called using studies wisely. And we kind of touched on this the other day. And Angeline, I think you were the one who asked, what is the cutoff? When do we decide that something is or is not statistically significant? What did you guys get when we did our fish oil? Did you guys have 1 or 2 dots out of 110 or something? What did you guys have? There was only one above? Right. Right, because it was 1 out of, I think you guys had 110. So I said it was less than 1%, okay? So I said those results would be statistically significant. And that's what Angelina asked. She goes, well, how do you know when the cutoff is? All right, we're going to talk more about that. I said here, there's a way that we can quantify it, but that's going to come later. But the bottom line is to be statistically significant. What we mean by that is results are so extreme that they likely could not have occurred simply by chance. So the data that I gave you for the fish oil example, it was when you did the X bar fish minus X bar regular, it was 7 point something, okay? You guys right away, when I gave you the handout and kind of gave you the background, I said, what do you think? Does it look like fish oil works or not? And it's yeah, it looks like, and most of the people, had a reduction. So yeah, I think it's working. But we conducted our experiment to decide, was that 7 point whatever, was it really that big of a reduction that we should be wow, let's prescribe fish oil? So you did your simulation, and only one time did you get a result that was that big or bigger, okay? So that's why I said 1 out of 110, less than 1% of the time, that would be statistically significant. That drop of 7 was huge from a statistical perspective, okay? So statistically significant just means those results are so extreme that I don't think that just happens. I think I have to conclude that it was due to whatever treatment I prescribed. I think the fish oil did it, okay? Now, When it comes to drawing other conclusions, it depends on how your experiment is set up, okay? You can randomly assign people to their treatments, and you maybe could have randomly selected the people to even participate. So let's talk about that first, because you think that has to happen first. The bottom line is, if individuals are randomly selected to participate in your experiment, you can make inferences about the population. You could come back and say, I think the results in my experiment, I think I can go back and say, even though I only did it in my sample, I think I could go back and say that it's true from the entire population from which I drew my sample, okay? If individuals are not randomly selected, okay, you do not make inferences about the population. All you can say is, well, it happened in this group, so yeah, this group, okay? Now, once you have your participants, whether they're volunteers, whether they were randomly selected, whether you picked them, whatever, if you randomly assign them to treatments, like I keep talking about, yes, randomly assigned to treatments, then you may talk cause and effect. Okay, you have to have random assignment to treatment if you want to talk cause and effect. If you think your treatment is better and you want to establish cause and effect, my treatment made those results happen, you have to have random assignment. If you do not have random assignment, you may not talk about cause and effect. And this chart is in your book. I think by default, I think almost anyone would agree, this is the best thing, okay? If you want to talk about the population, if you want to talk about cause and effect, you want random selection and you want random assignment, okay? Now you might say, well, why don't we just always do it that way? It's just not always feasible, okay? It's just not always feasible. But the bottom line is, if you don't have random selection, you have voluntary participation, or you just choose people, and if you don't randomly assign to treatments, if you're at a no-no situation, part of me would say, then why in the heck are you even conducting your experiment? You've really got no results that you can conclude other than right here, right now, okay? The short rule is this: random selection. You may make inferences about the population. So there was a diagram I gave you at one point that you take your sample and you can infer it back to the entire population. There's like a little arrow that was drawn here, okay? That's what we're talking about. You conduct your experiment on the sample, but you take the results and you push it back onto the population. If you have random assignment, you may talk about cause and effect. And I have some examples on the next page. I will tell you, most of the time what they'll do, if you see this on an AP test, they will literally give you a scenario, describe what happened, and then they'll ask you, which of these conclusions would be a valid, legitimate conclusion, okay? So this follows up on the concept of, does music help or hurt when you study, okay? So for each design, what we're gonna assume on this, we're gonna assume that we have our sample, we calculate their average GPAs, and I'm making this up. Let's say the average GPA, okay, GPA X bar, let's say that came out to be 3.8 before, and then after listening to music, the GPA for X bar, let's say it was 3.7, okay? Let's just say, okay, this says though, suppose that the mean GPA for students who listen to music was determined to be significantly lower. Okay, let's say the mean was lower. It dropped, it got lower. Okay, what could we conclude? All right, suppose the whole experiment was set up by just taking all the people in our AP class and we asked them do you or do you not study with music? And we let you guys put yourself in your own groups. You're like, I listen to music. Okay, you go over here. Oh, I don't listen to music. I go over here. If I just use all of you and I let you decide how you're going to put yourselves into groups, that means there was no random selection because I just used you, and there was no random assignment because I let you sort yourselves. You basically can't draw any conclusions, okay? You cannot talk about the population, no population inference, and you cannot talk about cause and effect. And again, my response on that would be, why are you even doing this? You can't do any inference. We can't go back and say that all high schoolers will do worse listening to music. Okay, we got nothing. Okay. Now, if I select a random sample of students from the school, but then I ask them to self-divide themselves, I got a little something here. I have random selection, but I don't have random assignment. So I still cannot make any cause and effect, but I could say that I could infer back to the population. And you might say, infer what? Well, if the scores went down listening to music in this group, I could say that in general, I think for high schoolers, scores will go down if high schoolers listen to music. There's a relationship. I could establish that. However, I can't establish cause and effect. Okay, then you might say, well, what is it? Well, you have to go back to the lurking variable sort of thing. Maybe it has to do with your learning style in general. Maybe it has nothing to do with, the music, but maybe the people who listen to music just happen to be more of a creative, artistic sort. And that maybe was the reason that their grades went down because, for whatever reason, that unit didn't mesh well. Okay. I could say that music definitely seemed to have an association here with grades going down, but I can't do cause and effect. And now I'm going to reverse it again. I'm going to say all of you are just you're my sample. No random selection. But now, if I literally, for every single one of you, and I flip a coin and say, heads will be music, tails is no music. So I flip a coin, heads. Okay, you're listening to music. Flip a coin, heads. Okay, you listen to music. Flip a coin, tails. Okay, you don't listen to music. If I randomly assign you, now also remember, if I'm randomly doing that, you realize it doesn't have to be a 50-50 split then. I could end up with 12 of you listen to music and 2 of you don't. Okay, you don't have to have a 50-50 split. But if I have no random selection, I have no population inference. So whatever results we get, I cannot go back and say, I think all high schoolers are like that. But because there was random assignment to the treatments, I could draw a cause and effect. And I could say for this group, I think the music might be the reason that your grades went down. Okay? Because I randomly assigned you to treatments, I could say that now I think that might be the reason your grades went down. Because remember, this is all based on the fact that we assume that the grades did go down. Okay? And of course, you can see what the only one left is going to be. A random sample, and if I randomly assign, now we got both. We have a random sample and random assignment. I can now infer back to the population, and I think I can infer cause and effect back. And I could now say that if I randomly select my sample and I randomly assign to treatments, now I can say, I think all high school students might have grades that will go down based on whether or not they listen to music. Okay? Again, I don't think anyone could argue that that's probably the most powerful right there. you want to have random selection, and then you want to randomly assign to treatments. And that's all section 3 is. There's only 5 questions. That's it. So it's super fast. All right.